Hey, welcome back to Calculus. In section 4.8, we're going to take a look at something called Newton's method, which is a numerical approximation algorithm to estimate zeros of functions to find solutions of equations of the form f of x equals 0. All right, so you can see the objectives in the screen there. I want to show you what Newton's method is, how to implement the algorithm. In a second video, separate from this one, I'm going to show you how to implement Newton's method in a spreadsheet, kind of like finding limits by tabling values. There's sort of some tedious, repetitious calculation that you have to do, which is sensitive to round-off error. So these things are perfect for programming. So I'm going to show you how you can do that in a spreadsheet, either Excel or Google Sheets or whatever your favorite spreadsheet is. And then just a quick word, why is Newton's method coming up in the middle of chapter 4? Chapter 4 is all about applications of the derivative to solve optimization problems. Well, you've solved enough optimization problems to know that in any one of them, you're always going to have to find critical values. You have to solve some equation like the derivative of some function equals 0. Yeah, and maybe the algebraic techniques that we know to find exact solutions to that equation won't work. But still, you need to know, well, what is the value of x, or at least what is a very good approximation of the value of x that makes my function 0? So that's what Newton's method does. Newton's method approximates solutions to equations. So it's coming up in this section, or in this chapter rather, because sometimes you're going to be looking for some critical values and the equation that you're trying to solve won't lend itself to algebraic methods. So Newton's method is something you can do to approximate those solutions. Okay, so let's get going. Let me introduce the method here just by via an example. So I've got some equation here. I've got an equation that's a cubic equation, x cubed minus x minus 1, and I want to know when it's 0. I've plotted the function x cubed minus x minus 1 over there, so I can see that from this graph that it's got a solution, and that solution is somewhere between x equals 1 and x equals 2. If I mark it on the axis right there, the x-coordinate of that point is what I'm looking for. Let me give it a name like x star. So I'm trying to find that x star. Okay, so what is the technique I'm going to use? Well, we're going to just pick a value near x star. We're going to choose some initial value. I'm going to pick it and call it 1. x1 is equal to 1. So I choose something there, and then I linearize at that point. So what do I mean by linearize? I take a look at the equation of the tangent line at the corresponding point to my first guess. Yeah, maybe that tangent line looks like that. So I find the linearization L of x. The linearization is a linear function, and a linear function is easy to find its x-intercept. The algebra involved in a linear function is easy. So this point that I'm marking right there that I'm going to call x2 is easy to find with algebra. And notice that x2 is a little bit closer to x star than x1 was. That's a good thing. So then what we'll do is from x2, we'll go up to the graph. I'll draw one more in here. We'll linearize again. We'll find the equation of the tangent line at that new point on the graph. Finding that tangent line in there, we'll linearize, and I won't even try to draw it in there, but if you can see the x-intercept of it, I'm going to call it x3. x3 is even closer to x star still. All right, so let me switch over to a Mathematica notebook I made. I like it. I want to show it to you. That illustrates the same kind of thing. So here we're looking at the same function. X star is the point on the x-axis. It's not marked in this picture, but it's where that green curve is crossing the x-axis, somewhere between 1 and, well, it looks like 1.5. And choosing x1 equal to 1, look at that black dot on the curve, and the red tangent line is the linearization there. And I've marked on here, you can see because of the scale, the linearization's x-intercept is 1.5. So if my initial guess for the solution of this equation was 1, my next guess is 1.5. And now I linearize at 1.5. So I take the corresponding point with that x-coordinate, find the equation of its tangent line, and solve for its x-intercept. I don't have it marked here, but it's closer to my initial value, or the desired value rather. And then I linearize there. Yeah, and then I linearize there. This picture gets kind of busy, but what's happening is those x-intercepts are all kind of getting super close to each other, the x-intercepts of the linearizations. So those x-intercepts of the linearizations should give me ways to approximate the solution to the equation I'm trying to solve. All right, so that's the geometry of it. Let's go back to the whiteboard and we'll see if we can't write down some of the mathematics. How do we calculate this, right? Because when someone's asking you to estimate solutions of an equation, you're not going to come back with a picture. You want to give them some number. So we've got the idea that we choose x1 near and we linearize and we generate a sequence. What do I mean by a sequence? Just informally, I mean a list of numbers, our initial guess, and then we replace it with the next one, we replace it with the next one. So in this sequence, we keep getting these numbers, and hopefully these numbers are going to get closer and closer to x star as we look at more and more of them. Yeah, that's our goal. We're going to generate this sequence, and hopefully its values are going to approximate or approach the value that we're trying to say what the solution is. Okay, so how do we write this stuff down, the linearization? Well, let's suppose that we have one of these points. We have one of these xn, f of xn, and I want to linearize there. So you remember the linearization formula from earlier in chapter 3. The linearization at a point is the function's value at that point plus the derivative at that point times x minus the x coordinate of that point. So there's our linearization. The sub n everywhere, don't be intimidated by it. It's just the nth number in my list. You know, so like maybe it's x1 if I'm trying to find x2, or maybe that sub n is 2 if I'm trying to find x3. Okay, and then to find the x-intercept of a line, you set the out. I mean, x-intercepts, you always set the output equal to 0. So to find the x-intercept, I'm just setting L of x equal to 0. But because this is a linear function, it's easy to solve it for x. It's easy to solve this thing for x. You can check my algebra. I could just be quiet here for a second, but all I did is I subtracted f of xn from both sides, and then I divided by f prime of xn. All right, so that would give me this expression, x minus xn is equal to that quotient, and then I added xn to both sides. Okay, so this is the formula that I'm after, and this formula tells me my new guess, xn plus 1, in terms of my old guess, xn. So if I had an x1, this formula tells me an x2. If I had an x2, this formula tells me x3, and so on. So this formula is what people typically call the Newton's method formula. What we're hoping is that as we iterate this formula, as we keep plugging values into the right-hand side of it to get the new guesses, that those new guesses approach some number. Let's look at our example. Let's go back to our example. All right, so our function, you guys recall, was this cubic, x cubed minus x minus 1. Its derivative is 3x squared minus 1. You can check that out. So what am I doing now? I'm looking at what this Newton's formula looks like for this specific function. Yeah, so Newton's formula says that the new guess, xn plus 1, is the old guess minus f of the old guess. So everywhere, the placeholder x in my polynomial for f, I'm putting the old guess, xn. So I've got to cube it, subtract it, subtract 1, divided by the derivative at the old guess. That is 3 times xn squared minus 1. All right, so if we start iterating this thing, we can start seeing how the values are going to be. Our initial guess, we said, was x1 is equal to 1. So everywhere in this formula that there's an xn, there's 4 places, I have to replace it with 1 and then compute it out. All right, so I won't walk through all the algebra. You can stop the video. I think you should make sure that if you start with x1 equal 1, plug it into this Newton's formula, you get that x2, the next value is 1.5. All right, so then what do? I take that 1.5, everywhere in the formula that there's an xn, I put it in. So there's a 1.5 there, 1.5 cubed minus 1.5, 3 times 1.5 squared, and so on. And then check this, stop the video and get out a calculator. Again, I'm going to show you in a separate video how to do this with a spreadsheet to kind of make it happen faster, but it's important to understand what's happening. My third guess is that number, 1.34783. So to find a new guess, I would take that number and blah, 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 plug it in. Don't round here. If you're using a handheld calculator and it shows you more digits than that, use them all. Because when you're doing subsequent calculations with rounded values, your error will start becoming a problem, okay? So use as many digits as you have available. It's tedious, but it's not hard, okay? So you can just iterate these formulas. So I did it before making this video, and I'll show you what my result was. We did this by hand. We got x2 equals 1.5. I showed you this one, 1.34783. And if I keep going, those are the results. Okay, notice that starting at x equals 5, at n equals 5, starting at this one, to the number of digits I'm displaying, those things aren't even changing anymore. So that's kind of evidence that our sequence of x's is converging, and the x value, well, to that many decimal places, I'll just take it to be that number, 1.3472. So that's the approximation of the x coordinate of that cubic function's x-intercept, and we did it by Newton's method. Okay, so again, I promise I'm going to make a spreadsheet video to show you how you can crank out tables like this. But for the first few examples, I would recommend you do it with a handheld calculator. I hope that you're going to take time to stop this video and at least reproduce the next couple of rows from this thing to make sure that you understand what's going on. All right, let's look at a couple of other examples just to, well, sorry, let's summarize this. I've got a summary here. I forgot about my own notes. So what is Newton's method? If you're trying to approximate the solutions to some equation, f of x equals 0, okay, what do you have to do? You have to pick an initial guess called x1. Sometimes the initial guess is called the seed, gets the recursive algorithm going. And then subsequent guesses are formed by that box formula. The new guess is the old one minus f of the old one divided by f prime of the old one. Okay, and I'm saying that's true for n equal 1 and more. So x1 tells you x2, x2 tells you x3, and so on. And if that sequence has a limit, then that limit is going to be a solution of our equation. So that's a summary of this method. Okay, now let's check it out in an example. Got an example here. I want to approximate the solutions to an equation like cosine x equals x. Which angles have the property that the cosine of them is the same as the angle itself? Well, Newton's method finds zeros. So the first thing I have to do is kind of recapitulate that. Let's define some function like x minus cos x, because our equation has a solution, cos x equals x, if and only if x minus cos x, if you just subtract it from both sides, is 0. So you can always take any equation and think about it as the 0 set of some function just by moving all the terms to one side. Okay, Newton's method requires the derivative. I computed it there. Hope you can check it, 1 plus sine x. So here's the Newton's formula in this particular example. It's old value minus f of old value, so that's xn minus cosine xn over the derivative, 1 plus sine of xn. And we need a guess. So how do you generate a guess? The method is actually sensitive to how good your first guess is. So you don't want to guess just completely randomly. A lot of times I would recommend you just use a graph. I'm going to switch over to Desmos here real quick. I've got this function plotted. So you're looking at a graph of the function x minus cos x. You can see that the 0 that we're trying to approximate is between 0 and 1. So why not we take the initial guess to be 1? Yeah, if I took an initial guess to be like -1 or 2 or 3, the method might still work. It's kind of subtle. We won't really get into the fine details of when this thing will or won't work. But generally speaking, the further away from the solution you're trying to approximate your first guess is, well, the algorithm has a higher chance of failing, or it'll take longer. So you kind of want to make your first guess as accurate as you can. I'm going to take mine to be 1. Just so I have some chance to illustrate this on paper in front of you. So let me switch back to our whiteboard. It's coming back here in just a moment. We're back. Okay, so from the graph, I'm going to take x1 to be 1. Okay, and now you verify this. I've just written them out, but if I take x1 to be 1, and everywhere in this formula that there's an x value, there's 4 spots. If I replace that x value with 1, making sure my calculator is in radian mode and carefully following the order of operations, I'll get that x2 is equal to 0.75036. Stop the video and make sure you can verify it. And then you take that x2 and you plug it in everywhere that there's an xn in your formula up there, and it'll tell you what x3 is, and so on. So check these, stop the video, take a few minutes and check them. And you can see by the time I switch from X4 to X5, the answer didn't change out to 5 decimal places. So I'm going to say, I'm going to take X star to be this number, 0.73909, right? So I'm claiming that the cosine of that number is that number, and it will be approximately equal because these are approximations. And I'm not really saying anything about controlling the error here, so I'm being a little bit sloppy mathematically, but I'm just saying if you run Newton's method until the digits stop changing out to a certain place, then you have accuracy to that place. Yeah, so in this case, 5 decimal place accuracy. Nice. All right, so watch the spreadsheet video to see how to automate that process. I'm going to do one more example. This video is getting a little long, but I just want to, as a disclaimer, say that Newton's method can fail. All right, Newton's method won't always work. It can fail. Why does it fail sometimes? Well, it's a little bit subtle, but it can fail for different reasons. One of the reasons that Newton's method might fail is that you might, as you're generating your sequence, find some number, xn, that makes the derivative 0. Well, that derivative is in the denominator, or if you think about it, a horizontal tangent line doesn't have an x-intercept. So if you ever hit an xn where the derivative is 0, the process is just going to stop. You're not going to be able to produce xn plus 1. So if that happens, just to change the seed, try it again. Sort of, you just had some bad luck. But it can fail for even worse reasons. The shape of the graph can be such a thing that Newton's method just won't converge. Here I've got kind of a picture. I'll try to do a couple of these by hand, and then I'll show you in Mathematica, and we'll end this video. But this is a graph of the cube root function. Hopefully you know what number makes the cube root 0, but if I were trying to approximate that with Newton's method, I might do something like this. I might pick an initial seed, x1, and then linearize there. Maybe, yeah, I'll linearize there. So I need to draw the tangent line through that point. Let's approximate it like that. And then what's my new approximation? Well, it's this number over here, x2. And you probably already have a sense that things didn't go well here. If we take our x2 and we linearize again through there, can you see what's happening? These numbers that I'm generating, x1, x2, I just found x3, they're not getting closer to my desired point. They're getting further away. So what's responsible for that? It's the shape of the graph. This is kind of subtle business, and we won't get into it in too much detail in this first semester calculus class, but here I can just kind of animate what I just did. I've got the cube root function drawn. It's in green on this screen. I've linearized somewhere. It looks like it was at around, I don't know, 0.5 or something. It doesn't really matter. And there's my next solution. It's further from the origin than my first one is. And then I linearize there, and the blue dot gets even further. Linearize again, now it's all the way out to -4. If I linearize again, it's not even in the picture. So that's a kind of the shape of this graph. That vertical tangent line at the origin is kind of forcing this sequence is diverging. It's not even going to converge. Okay, well, so tune into the video to implement Newton's method with a spreadsheet, and thanks for listening.